Let's begin. Today's talk is Unity Object Fundamentals. I deliberately chose a back-to-basics topic this year. The UnityEngine.Object class in the familiar Unity Engine namespace is often used without a clear understanding of what it really is. Its role, serialization, and memory management mechanisms are rarely covered in tutorials or introductory books. Many people are dropped into Unity, learn by feel, and continue with only a vague understanding. Today, we'll examine those details and reveal how they really work. Ideally, you would know this from the start, but it is omitted to avoid overwhelming beginners. Today, I'll give you the fuller explanation those introductions leave out. Intermediate Unity users should have moments where things click, while advanced users may already know much of this. Even so, it should be useful as a review and fact check, so please stay with me. First, let's define more precisely what I mean today by a Unity object. Put simply, it is UnityEngine.Object. That is the base object class in the Unity Engine namespace. Many different classes derive from it: texture, mesh, monobehavior, and many others. So it appears that object is the parent of them all. But first, let me clarify what actually happens behind that impression. Let's divide the world into native code and C#. The native side is the Unity Engine C++ implementation. The C# side is mainly the script code you write. The C# side contains the UnityEngine.Object class. In practice, each one has a one-to-one counterpart, a built-in object class implemented in native C++. These two objects are linked by a shared 32-bit instance ID. On the C# side, that's the value you get from the object's getInstanceId method. This native object holds a GC handle that points to the C# object. From C#, it keeps a raw pointer as M cached pointer, so it can reference it. On the native side, there's also an ID to pointer table for looking up an object pointer from an instance ID. The native side also provides PPTR, a smart pointer or pointer wrapper that safely gets an object pointer from an instance ID. PPTR shows up often in error logs and stack traces. You won't use it directly, but it's worth knowing the name. Basically, classes provided by Unity Engine come in pairs that inherit from these built-in classes. For example, Mesh has a native Mesh class derived from Object, and a C# Mesh class derived from Object. And of course, Monobehavior also has a native Monobehavior class. Scriptable Object is a little different, though. On the native side, it's associated with the Monobehavior class. Functionally, Monobehavior and Scriptable Object are almost the same. The main difference is whether they exist in a scene or independently as assets. And from those two classes, many user scripts are derived. This huge set of C++ and C# class pairs is what makes up the Unity Engine's functionality. The Unity Engine creates instances from these classes, keeps them alive, and destroys them when they're no longer needed. And as I explained earlier, those instances refer to each other using instance IDs. The important point is that Unity can serialize this whole set of instances, including those cross-references. In other words, it can save that set of instances to a file or to memory. And of course, deserialize it too. That means Unity can restore this state from data saved in a file, including all cross-references. This mechanism is used not only for saving scenes, but throughout Unity. I'll explain that in more detail later. To summarize, Unity provides its features through classes derived from UnityEngine.Object. It manages their lifecycle, and it provides serialization for saving and restoring them. I think this is Unity's essence. Put another way, if a class doesn't need Unity to manage its lifecycle and doesn't need save and restore, you can choose not to use a UnityEngine.Object. Inside Unity, examples include logger classes and command buffer classes used in rendering. Those classes don't need serialization, and their life cycles are handled specially, so they're actually implemented without using UnityEngine.Object. With that foundation in place, let's look a bit more closely at the life cycle of a UnityEngine.Object. Creating a UnityEngine.Object creates native and C# instances. They are then assigned a shared instance ID. For instances loaded from a file, like objects placed in a scene, that instance ID is positive. Instances created dynamically at runtime have negative values. Positive IDs count up from 1. Negative IDs count down from -1. Rules here have exception, so be cautious. IDs are assigned in creation order, so they can generally differ from run to run. Slight creation order changes also change IDs, so you can't assume an object always created 10th will always have instance ID 10. Once both are created, their cross-references are established. Native GC handle, C# raw pointer. Loaded objects are deserialized, others are initialized. I'll explain deserialization later. Then it's registered in the pointer map for instance ID lookup. At the same time, there's also a type-to-object set mapping, and it gets registered there too. That's what methods like findObjectByType use. A few smaller things also happen here, but in broad terms, after all that, awake is called to finish things up. People sometimes ask about the difference between start and awake, and it's fine to think of awake as the final step of object setup. Start belongs more on the update processing side. Next, let's look at UnityEngine.Object destruction. Destruction involves more parts, so it's much more complex. First, the basic flow. First, someone on the C# side starts destruction by calling object, destroy. There is also destroy immediate, but if you use plain destroy instead, the object is queued for deferred destruction, not deleted immediately. Then at the end of that frame's update processing, all objects queued in the deferred buffer are destroyed together. When the object is actually destroyed, familiar C# callbacks like onDestroy run first. Next, the native side object is destroyed. The C++ destructor runs, and the native memory for it is freed. The GC handle on the C# side also becomes unusable here. It's also unregistered from the various mappings, things like the ID to pointer map, and the type-to-object set stop tracking it. That makes the instance ID effectively unusable. Then the C# objects cleanup runs. The raw native side M cache pointer is also cleared. And that's the end of it, but it still feels a bit awkward. Because the C# object is a managed object, its actual destruction, its real memory release, has to wait for garbage collection. Until the GC collects it, the object remains as a half-dead zombie with its native half gone. And if some other object still references it, then even when GC runs, it still has a reference, so it won't be collected and will remain. That's the issue often called leaked managed objects in Unity. By the way, if M cached pointer is null, then comparing null with a reference to this C# managed object returns true through some very unusual built-in behavior. That's the infamous fake null behavior of Unity objects. In C#, the object is still alive, but in Unity terms it needs to look dead. So they went with this rather evil design where comparing the reference to null returns true. And at this point, it's mostly just a source of confusion. So as you can see, object destruction is managed very differently on the native side and the C# side. And the timing is very different too, which easily causes confusion and trouble. Now, this destroy process can also run automatically, not just when you call destroy yourself. That's asset garbage collection, or asset GC. If I call asset GC, unload unused assets, you'll probably recognize it right away. This one's more familiar, right? It finds unused assets and disposes of them together. Asset GC is separate from C# GC. From Unity's point of view, it finds unused UnityEngine.Objects and destroys them together. That's because Unity objects may hold strong internal references through raw pointers or GC handles, while elsewhere they use instance IDs or weak references through smart pointers. Existing GC has a lot of caveats, so it's basically a custom implementation to overcome that. Asset GC uses mark and sweep. First, it takes objects in the scene and manager objects as roots, follows references from them, and marks every reachable object. Here it accesses the C# VM and investigates deeply. Parts of Mono were customized for this. It scans everything. References from Mono behaviors, static variables, singleton classes, and even indirect references held natively through PPTR. Then unmarked objects are deemed unnecessary and collected in the sweep phase. This asset GC runs when you switch scenes, like a normal non-additive load scene, or when you manually call unload unused assets, or when memory pressure gets severe in the editor. And as you all know, this asset GC is extremely heavy. Because it has to access the VM's internal state, it needs a stop-the-world pause that temporarily halts all managed C# threads. So for a certain amount of time, every managed thread has to stop for this. If you don't want your game to stop even for a single frame, this can become a bottleneck. To avoid that, some projects build everything around additive scene loading, or even avoid scene loading entirely. Ultimately, I think that's an option too. That makes it a lot harder than the development experience Unity normally expects. But with careful design and implementation, I think it's doable. Quite a few teams already do this. Now let's dig into Unity object serialization. First, a Unity scene data file in YAML. By inspecting it, we can see how the data gets serialized. So here's a scene file stored in the Assets folder, in this case, GUID Unity. Let's open it in a text editor. Open it and you'll see this inside. A typical YAML file. This is a scene file. Scroll to a clearer section, and this part gets easier to follow. It stores each component's field values, and you can see things like X, Y, and Z. For references, you see things like file IDs and GUIDs, which probably define references between objects. You can tell. First, let's look at the file ID. The name file ID sounds like a file descriptor, but it's actually different. It indicates which object stored in the file is being referenced. Within that file, it works as each object's local ID at file scope. The name file ID is a bit misleading, so let's call it LFID. Unity calls it LFID too, and every object stored in the YAML has an LFID at the top as an anchor. That and something is the LFID. If we look at a specific internal reference, for example, the third entry in this reference component, the one with file ID 303, you can see LFID 303 here. That means it refers to this mesh renderer. And this game object has file ID 302, And since LFID 302 is here, that tells us it refers to this game object. So that's how it works. References within the same file can be resolved using just the LFID. So what about references to external files? For example, this mesh filter refers to a mesh object in an external asset file. In that case, the LFID and GUID are both written. This GUID is the ID assigned to each asset file. And you know those meta files generated next to each asset file. We can inspect the meta file for the obj model used by that object and open it in a text editor. It's a YAML file like this, and you can see the earlier GUID here. With this LFID and GUID pair, you can uniquely refer to a specific object inside an external asset file. Using a GUID instead of a path preserves the reference even if the file or path changes. It's one of Unity's familiar core features, and it's implemented with this LFID and GUID pair. By the way, GUIDs are only used in the editor. In a built player, GUIDs are not used. File paths are used instead, more later. Now, object references also list a type alongside the LFID and GUID. This indicates how the imported object exists. Type 2 is a serialized asset type, and Type 3 is a meta asset type. A serialized asset means the serialized YAML file itself is actually there. It means the YAML data file itself exists in assets. Materials and scriptable objects are serialized assets. For example, this is referencing a material in materials, and if you open that file in a text editor, it looks like this inside. The contents are YAML, so you can see the serialized asset file itself is right there. By contrast with a meta asset, what exists in the assets folder is the imported source file, and the serialized data file is stored somewhere else. For example, the mesh object referenced here by this mesh filter was imported as an obj model file. Let's trace that conversion. First, we have the usual assets folder, and we drop in a mesh obj file. Unity imports it, converts it into a mesh object, serializes it, and saves it in the library artifacts folder. In the editor, this serialized data is what gets referenced. That's the meta asset system, but meshes aren't always meta assets. For example, assets made by editor scripts or duplicated out of model files with Ctrl+D or CMD+D exist in the assets folder as serialized assets. An extracted file opens as YAML in a text editor, so even a mesh can sometimes be YAML. One more unusual case, a rare one, is when an asset is embedded inside serialized data. An editor script can create a scene-only mesh instead of saving it as an asset file. Saving the scene embeds that mesh directly in the scene. Its serialized data is appended to the scene YAML and referenced only by its LFID, without a GUID. If you do this, the serialized data naturally keeps growing with the mesh data. So I don't really recommend it, but it is one option. And there actually are assets and plugins that use this approach. So GUID and LFID can reference assets. Unity also has a runtime mechanism for managing those references, called the remapper. Put simply, the remapper maps assets to the instances created from them. You can cross-identify an asset ID and a loaded object's instance ID. In the editor, LFID GUID pairs map to instance IDs, and vice versa. This remapper lets you reference already loaded assets. It also tells if needed assets are already loaded. For Unity assets, I'll explain this later, but they are basically preloaded in batches ahead of time. So there are not that many situations where you need this kind of dynamic check. But asset bundles, for example, are loaded and unloaded dynamically. So identification like this is needed. In the editor, when an object is serialized and saved, it's used to check where the destination file is, and serializes object references as GUID and LFID pairs. An interesting remapper feature is giving instances from the same asset the same instance ID. For example, if you swap a model file while play mode is running in the editor, the mesh is replaced immediately. The mesh is recreated at runtime, so its instance ID would normally change, but here, the remapper does special handling to assign the same instance ID, which preserves the reference. It seems natural, but it's odd if you know instance IDs normally increment. And the inside story is that Unity had this remapper to solve it cleanly. This remapper is also used when loading scenes, but that's special. After loading, scene hierarchy entries are removed from the remapper. It seems odd, but Unity scenes can be loaded additively, right? So you can keep creating more instances, which means you can't map assets and instances one-to-one. Because of that limitation, they're unregistered from the remapper, and scene unload processing doesn't use it either. Now that we've covered the background, let's finally move on to serialization. When you're writing mono-behavior or scriptable object code in C#, the usual assumption is that public fields and fields marked with serialize field are automatically serialized. But in reality, most built-in classes in Unity do their serialization on the C++ side. C# auto-serialization only covers mono-behavior, scriptable object, scripted importer, and subclasses. You don't usually need to think about that difference, but classes implemented on the Unity Engine side follow completely different serialization rules from your C# classes, and knowing that helps explain some otherwise mysterious behavior. Now, as for what this automatic C# side serialization actually covers, it looks like this. I copied this straight from the documentation. Only matching fields are auto-serialized. Most of you probably know this already, but in some special cases, not just public fields but private fields can also be serialized. I'll explain it later. Unity automatically serializes these fields, but the mechanism is implemented on the native side without using C#. From a typical C# programming perspective, you might imagine it inspecting the field layout with C# reflection, and then accessing each value. But Unity serialization uses no reflection. Unity first generates layout metadata called typetree for each class it serializes. For each class, the typetree stores the names, types, and offsets of the fields Unity serializes. Then during serialization and deserialization, the C++ native side uses that typetree to read and write those field values directly. So from the C++ side, data gets read and written through a path it cannot really see, which feels a bit strange. That is one reason the behavior can feel unintuitive from a C++ perspective. Next, when Unity serializes and deserializes. This is quite common. It spans an enormous range. Saving and loading scenes or asset bundles, project builds, and asset import are the usual serialization cases. And in the editor, right before entering play mode, Unity also serializes the whole scene to back up the current editing state. The actual flow's complex. Here's the diagram. Right before play mode starts, if the scene has unsaved changes, Unity serializes it to create a backup. After that, as I'll explain later, a C# domain reload happens here, which also triggers large-scale serialization and deserialization. Then Unity discards the entire scene, reloads it from the backup, and rebuilds it. That domain reload and full scene reload are support steps to make play mode behave more like a built player. In editor settings under Enter Play Mode settings, if you choose not to reload the domain or scene, you can skip those steps. Otherwise, serialization runs a lot of times. Serialization also drives inspector display and editing. As I mentioned earlier, the inspector reads and writes values through an unmanaged path without using reflection, and that relies on serialization. Serialization is also used for editor actions like copy and paste, undo and redo. Serialization handles nearly all state saving and restoration. Instantiating an object also means duplicating its state, so that goes through serialization too. This happens not only in the editor, but in built players too, so watch out. Instantiating a huge object serializes, then deserializes it, adding an extra round trip. Performance-wise, it can become a serious concern. Asset GC also uses serialization, while it examines object reference dependencies. And the most complicated case is C# domain reload, or hot reload. This is the process that applies changes after C# scripts are recompiled. Unity C# domain reload, also called hot reload, destroys and rebuilds the net app domain, then applies the contents of the newly recompiled C# scripts. Basically, the entire C# runtime is torn down and rebuilt from scratch. On top of that, Unity tries to preserve the state of objects like mono-behavior and scriptable object as much as possible across the domain reload. As you all know, that doesn't always go smoothly, but let's look at how it's implemented. First, things like script updates or entering play mode trigger the start of a domain reload. First, a series of C# shutdown steps runs. The before assembly reload event is called, and each script gets onDisable called. The objects aren't destroyed, so onDestroy isn't called. So onDisable gets called instead. Then Unity serializes the state of every existing mono behavior and scriptable object. That includes ones not referenced from the scene. Basically, anything serializable gets serialized here. One thing to watch here, not just public fields and serialized fields, but private fields too get serialized. Fields you do not want serialized must use the non-serialized attribute. And finally, the C# objects are destroyed. What matters here is that the native side objects remain intact. UnityEngine.Object exists as a native and C# pair, but at this point only the C# side is wiped out. Then GC and finalizers run, and once everything is cleared out, the app domain is unloaded. After a new app domain is created, the assemblies are loaded, the C# objects are rebuilt, and their pairing with the native side is restored. Then the saved state is restored through deserialization, resume processing runs, and the domain reload is complete. To carry state across like this, Unity uses special serialization here, including private fields. Honestly, state restoration often does not work well. Even though it includes private fields, any data in classes the serializer does not support is lost here, and even some basic C# features, like value tuples, are not supported by serialization. So in practice, you lose information at a pretty basic level. You could intercept serialization callbacks here, and manually serialize all the unsupported data. But doing all that just for hot reload support is hard to justify. So, in many cases, people give up on supporting hot reloading during play. Next, let's look at the storage formats used after serialization. First is the YAML text we've already seen. This is editor only. It is human readable and flexible, but processing speed has its limits. Second is the binary format. This is used mainly at runtime. Two binary format versions. One is an unsafe format without type tree, and the other is a safe format with type tree attached. The unsafe format assumes the serialized data exactly matches the runtime code's data layout. It just reads the fields in order, so loading is simple, fast, and lightweight. This is the main format used in built players. It's fast but can't handle data layout changes. If a field is added or removed, or even if the field order changes, compatibility is lost. The safe binary format covers that weakness. By attaching type tree, it can absorb differences in data layout. This format is used when data imported in the editor is stored in the library artifacts folder, and by default. Asset bundles also use this safe format. The downside of the safe format is slower loading. Naturally, checking the type tree and reconciling layout differences adds overhead and increases memory use. In practice, if you switch an asset bundle from unsafe back to safe, load times usually get longer. So when load time is critical, you may have to give up convenience and use the unsafe format. That's the trade-off. Also, type tree can handle simple layout differences like fields being added, removed, or reordered. But beyond that, it can't handle everything. If a name changes or the same name changes meaning, that's beyond layout, so type tree can't handle it. That's why people say asset bundles should be rebuilt every time you upgrade Unity, even if they use the safe format. The reason is that if the Unity engine side changes in certain ways, things can break. In most cases, the safe Type 3 format should cover it, since that's already accounted for, but for safety. If safety matters that much, you have to say, rebuild all asset bundles every time you upgrade Unity. So it comes down to which costs more, rebuilding the asset bundles or verifying the safety. By the way, this came up in the roadmap session too. Unity plans several improvements to Asset Bundle Type 3 in future versions. Up to now, Unity loaded every Type 3 attached to an asset bundle and expanded all of them in memory. But with this improvement, the same Type 3 won't load twice. Surprisingly, until now, even duplicate Type 3 data was all loaded into memory. Unity 6.3 already has this improvement. So if you loaded lots of asset bundles with the same type, Type 3 used to inflate memory usage, and this may reduce that problem. And in Unity 6.5, Type 3 is expected to be moved out of the asset bundle entirely, which should reduce storage use and even build size. With changes like these, we may be reaching a point where it's worth reconsidering whether using Type 3 is simply the better option. Back to serialization formats, JSON is another option. Unity Editor doesn't use it as a core feature, but some external packages like visual scripting do use it. This JSON format is the only serialization available to users at runtime. So if you want to save object state at runtime, you'll use this, but there are limits. It only serializes user mono behavior and scriptable objects. And references to objects are stored as instance IDs, so they stop working across sessions. Basically, references last only until the app closes. There are various constraints. Think of it as limited runtime-only serialization. One more thing to mention is the Unity archive file format. This format bundles serialized files into an archive, mainly for asset bundles. It's also used when a player build option is enabled that compresses serialized files together. You can inspect this archive format, the one used by asset bundles, with a tool that ships with the Unity editor called WebExtract. You can use it for analysis. The WebExtract command is in the Tools directory under the Unity install folder. If you pass an archive file, like an asset bundle, to WebExtract, it expands the contents like this. For a normal asset bundle, it extracts a serialized binary file named cabguid. The extracted asset bundle binaries and files in a player build's data directory, such as level 0 and shared asset 0. Assets are serialized files in the binary format I explained earlier. There are also tools for analyzing those files. That's binary to text. This one is also in the Tools directory. If you pass a binary serialized file to this command, it converts the contents into human-readable text. If you analyze with this, I recommend enabling type tree first. It can still force a conversion without type tree, but you lose the data details, so it's not very useful. For asset bundles, build options control it, and player builds also have a Unity editor option to force, including type tree. In the diagnostics options, turn on the switch called Force Always Write Type Trees. That should make player builds include type tree data too. If it doesn't, try restarting the editor or deleting the library folder once. It seems to fail sometimes, but it should work, so keep trying. Using these tools, I converted the file named Level 0 in a player build into text. With Type 3, we can clearly see inside. This file, Level 0, contains each scene's content serialized almost as is. If you look inside, you can see game objects, transforms, monobehaviors, and so on. Unlike the editor's YAML, object references are handled differently here. In the editor, we used LFID and GUID, but in a built player it uses file paths instead of GUIDs. That's why the paths of externally referenced files are listed at the top. Then in the actual references, you see a file ID and a path ID. This is a bit confusing, sorry, but the file ID here means which entry in that external reference list it points to. If the index is 0, it means an internal reference in this file. And this path ID is the LFID. This is the LFID here. For example, file ID 0 means an internal reference here, and LFID 18 matches ID 18 right here. That tells us it's referencing this transform. Next, I converted shared assets 0 assets to text. This is the serialized collection of assets used by Level 0. If you look inside, you can see things like materials and texture2D assets. This preload data section at the top is a table for making loading more efficient. It lists the external files this file depends on. Loading dependency files separately on demand would be inefficient, so they're grouped up front as much as possible in a linear layout, so they can be loaded efficiently. Still, this really comes from the days when media with very slow random access, like DVDs, BD-ROMs, and CD-ROMs, were the norm. It still has that feel. With SSDs, you could argue that on-demand random access is fine, but Unity still takes care to pack things together like this. Another difference is the stream data. For data that can get large, like texture image data or mesh vertex data, Unity doesn't embed it directly in the serialized file. Instead, it's moved out into an external RAISS file. This RAISS file has no real format. It's just raw binary data dumped and concatenated, so bytes 0 through 575 contain this texture's image data. Next is the scene file, Level 1. Its external reference list adds shared assets 1 alongside shared assets 0. So assets used in the previous level stay shared through the previous file, while new assets introduced in Level 1 go into shared assets 1. That way, the same asset doesn't get serialized redundantly on disk. Next, let's look inside an asset bundle file the same way, using binary to text. First, the external references are listed. This asset bundle depends on other asset bundles, and those dependencies are registered as external references. To make cross-asset bundle references work, the referenced asset bundle has to be loaded and mounted. It only has to be mounted before the preload step. If preload runs first, the external reference becomes missing. After that, the assets are serialized like this with LFIDs. But in an asset bundle, that LFID is based on the original files. GUID and LFID combined and hashed. Very hash-like, right? Because if you simply assign LFIDs sequentially from the top, changing the layout, say by inserting an asset into an asset bundle, if you add or remove files, the LFIDs shift and external references can shift with them, which could break those references. Changing one asset bundle's layout would then require rebuilding every bundle to preserve external references. To avoid that hassle, Unity deliberately uses hashing here. Using hashes makes it resilient to some degree of layout changes. Also, every asset bundle always has LFID1. That ID is fixed. LFID1 stores the asset bundle object itself. This is just LFID1's asset bundle section. First, there's the preload table we talked about earlier for loading things together. Then in mcontainer, you have the list of assets stored in this asset bundle. This asset bundle only contains one asset, named material, and here is the setting for preloading the assets that this material depends on. Load 3 entries starting from index 0 in the preload table. That's configured here. The asset itself has file ID 0, so it's an internal reference within this file, with this hashed LFID. That's it. The rest is just optional info, like main assets. Now that we've looked inside an asset bundle, let's also go over its lifecycle. To use an asset bundle, call load from file or another load from API. Despite the name, these APIs do not load objects yet. Instead, they mount this archive's contents into Unity's virtual file system, VFS, under an archive/path, so the system can see that file path and what each LFID in it points to. It generally doesn't load the assets inside yet. The only thing deserialized at that point is the asset bundle object at LFID1. As we saw earlier, this asset bundle object contains a table for preloading assets in the bundle, so it enables name-based asset loading and gets things into a ready state. Then when you call load asset, or when another asset bundle that depends on this one performs a preload, these contents, the individual asset objects, are deserialized. Those deserialized instances are tracked by the remapper, so if a preload happens through another dependency, it can reference the same instance instead of loading a new one. That prevents this asset from being loaded twice. When this asset bundle is no longer needed, the user can call unload. This unload method has a Boolean argument called unloadAllLoadedObjects, and if you pass true, the loaded instances are all forcibly destroyed. If you pass false, it leaves all the instances as they are and exits. First, let's see forced destruction by passing true. The asset bundle is detached from the system, and the loaded instances are forcibly destroyed too. External references then become missing. If you pass false instead, those instances are left in place, and only the asset bundle is detached and unregistered from the remapper. External references to those loaded instances can still be used. But to destroy those instances, you have to wait for asset GC to collect them automatically. In other words, drop those references, then wait for asset GC. Also, the remapper has already forgotten that instance. So, if you load the same asset bundle again, it creates a different instance. In other words, you end up loading the same asset twice. So, cleanup for asset bundles has some inflexible parts, and it's fairly complex. If you need explicit resource management, leaving everything to asset GC is hard to justify. So in practice, you usually pass true to unload and force destruction. Also, as you've seen, if an asset bundle contains multiple assets, there's no way to select and destroy only one specific asset. It doesn't exist. For example, with 2 assets here, you can't force destroy just this one. If you want to do that, you need to split those assets into separate asset bundles based on their asset lifecycle. That's also necessary. Finally, let me touch on how asynchronous loading works. What we've learned makes this quick to follow. Unity's async APIs include load scene async and asset bundle, load asset async. This work is split across 2 background threads, the preload manager thread and the async thread. The preload manager handles general loading and deserialization for large binary data like textures and meshes. As I mentioned earlier, those are separated into res files, and loading those is delegated to the async thread. These threads handle everything from file reads through deserialization. You might wonder whether adding more threads would help. There actually is, but for now these two threads handle the background work. Objects deserialized on those threads are first placed into a queue. Then they reach main or render thread. The main thread reads this queue, integrates each object, and calls awake so the engine can use it. The render thread then does work like uploading mesh and texture data to the GPU. So while much of loading is offloaded to background threads, the final integration and the upload still have to happen. On the main thread or the render thread, if the load there gets too heavy, then even if the background threads did a great job, it still blocks at that point and causes stuttering. So we provide a way to tune the budget for that integration work. That is application background loading priority. At default normal, it's up to 10 ms per frame. Low cuts that to 2 ms. In theory, this lets you trade off async loading speed against frame stalls. But in practice, it often does not work that cleanly. Even if you raise the priority, file I/O or deserialization can still be the bottleneck, so behavior may not change much. And if you lower the priority, awake processing can still be too coarse and often block the thread. My impression is that adjusting this priority often is not enough. You usually need more asset-side optimization. Separately from that priority, quality settings also provides a way to tune the budget for uploads from the render thread. Honestly, though, that is also very hard to tune effectively, so I will skip the details here. There's a detailed blog post on this, so check it out if interested. And it ends abruptly. There are other features I couldn't cover today, like loading scenes from an asset bundle, which is handled differently. Which is tricky, but there's no time left, so I'll save it for next time. Today's roadmap touched on it. Going forward with ECS for all, entities will work much more closely with game objects. I can't say much yet, but entity IDs and instance IDs may become closely linked, and improvements are coming in this area. There's a lot more coming, and I hope by next year's event we'll be able to discuss it properly. I'll end by teasing that. Thank you.